Example, Otto cycle. An Otto cycle having a compression ratio of 9:1 uses air as the working fluid. Initially, pressure is 95 kPa, temperature 17 degrees Celsius, and volume is 3.8 liters. During the heat addition process, 7.5 kJ of heat are added. Determine all temperature in Kelvin and pressure in kilopascal, the thermal efficiency in percentage, and the mean effective pressure in kilopascal. First, we are going to draw the PV diagram representing the Otto cycle. Next, we are going to list out all the informations given by this question. We have the compression ratio. Compression ratio is denoted by RV. It is the ratio between the maximum volume to the minimum volume. The maximum volume is occur at state 1 and 4, while the minimum volume is at state 2 and 3. The value for the compression ratio given is 9:1. Also given to us is the pressure at state 1, 95 kPa. The temperature at state 1, 17 degrees Celsius. This value should be converted into unit Kelvin since the working fluid used in this cycle is air. The initial volume 3.8 liters. And we know that volume at state 1 is similar with volume at state 4. Note that given to us the volume is in unit liter, thus we need to convert liters into meter cube. And lastly, given to us by the question is the heat transfer in to our system 7.5 kilojoule. Next, we are going to analyze for each processes. Process 1 to 2, which is the isentropic compression. We can use the isentropic relation to find the temperature and pressure at state 2. Next, we are going to analyze process 2 to 3 to find other properties. Note that for internal combustion engine, there will be heat transfer in and heat transfer out for our system. For process 2 to 3, it is isochoric heat transfer in. The volume at state 2 is equal to the volume at state 3 for this heat addition process. We know that the value for the Q in is equal to 7.5 kilojoule. We know that to find the heat transfer in will be this equation. Note that this equation was obtained from the non-flow energy equation NFEE. By using the ideal gas equation of state, we are going to find the value for the mass. Next, we are going to substitute all the required values and we are going to find the temperature at state 3. For isochoric process, we can use the law of P over T is equal to constant. Thus, we can use the relationship between P2 over T2 is equal to P3 over T3. And now, we can determine the value for the pressure at state 3. Next, we are going to look into process 3 to 4, isentropic expansion. Since this process performs isentropically, therefore, we can use the isentropic relation to find the temperature at state 4 and pressure at state 4. Note that V3 over V4 is equal to 1 over the compression ratio RV. Now, we have already obtained the temperature and pressure for state 1, state 2, state 3 and state 4. Next item is to find the thermal efficiency for the cycle. The thermal efficiency can be determined by using the equation of work net out divided with Q in. For a cycle, work net out will be equal to Q net in, and Q net in is equal to Q in minus Q out. Thus, we can determine the thermal efficiency by using the formula of 1 minus Q out over Q in. Now we can obtain the value for the thermal efficiency for the cycle. For the mean effective pressure, it can be determined by using the formula of work net out divided with volume max minus volume mean. The value for the work net out can be determined by using this relation. The maximum volume has been given by this question. We're going to use the compression ratio formula to find the minimum volume for the cycle. Once we have all the required values, we can now calculate for the mean effective pressure.